this note 4, and we have also seen the first chapter. Okay, the first chapter of this note 4 was for this introduction and some of the ideas about the reservoirs, different reservoirs, and some other background information also, what we have seen earlier, what we have learned earlier from the other notes. And I have excluded some of the notes, and I have only concentrated on those notes, those things which you have not discussed earlier, you have not read earlier, and some of the items which you need to know, okay, which will help you to understand the CBM reservoir in more easy way. Okay, so with continuation of that, we will be starting with second chapter today. And with this second chapter, as you can see, that here also will be choosing some of the topics, and will not be continuing into all the topics. And some of the topics is already been discussed in the earlier notes. So let's start with this chapter second. Okay. And before starting, let me tell you that this is the extra class, and with this also, Wednesday at 10 a.m. as your CR has confirmed, and you have also agreed with this, that this Wednesday on 24th on 10 a.m. there will be another extra class, and I'll try to finalize your teachings, finalize the classes, the theory classes within the first week of February, and on this 8, 9, and 10. Okay, your class 12 up to 12 is the total class limit. Okay, the theory class should be done with on 12th March. So within this 8, 9, and 10th March, they will be scheduled for your Viva. Okay, the 8, 9, and 10th March is will be kept for the Viva for with the total syllabus. Okay, I'll be also notifying the same in the WhatsApp group, but be sure that by the first week of February, your total theory classes will be done, and so 8, 9, 10 will be your Viva. Okay, and after that you will be on your own for laboratory classes and all other classes, but there will be no theory classes. We have to complete the theory classes by 12th. Okay, and so I have taken so many extra class, and I am also requesting to take some of the extra classes. So please bear with me, because you know this is the current situation, and I don't want to disturb you after 12th, because you will be too much busy with your practical work or your project work. Okay. Let's start with the discussion now. Now, in this summary, this gas in place calculation, okay, the normal equation of this gas in place you have already learned. So I'll be skipping this. I'll be only discussing the error part, okay. And if you have remembered in the note 1, when we have discussed about the storage of the CBM reservoir, storage related to the CBM reservoir, you have seen that there are certain parameters. Okay, what are the parameters? The parameters are, as you can see from this equation, that it is related to the area, which is the drainage area or the reservoir area. Okay, this is another depending on this H is the reservoir thickness. Okay, the reservoir thickness, it may be of the gross thickness, and it may be depending on the net thickness. Net thickness, what is the difference between the gross thickness and the net thickness? Gross thickness is the actual thickness of the seam, whereas the net thickness is some part of the, maybe the total part or some part of the actual thickness, which is actually giving you the production, gas production. That is called the net thickness. And then it is the density, average density of the in situ rock. Okay, and then finally is the average gas content. Average gas content in the in situ. Remember that it is the in situ gas content. Whatever we are going to measure in the laboratory or in the desorption canister in the surface, that is somewhat different than the in situ gas content, because the temperature and the pressure both are different when you parameters, and we'll be discussing what are the types of the that is going to be occur, that is going to occur now. You can see in this example 2.1 gas in place at the coal site or some field data site, they have shown you the example how to calculate and what to calculate the gas in place calculation. Okay, to consider the gas in place calculation. So I request all of you to go through this example. Okay, you may not be able to find the Excel data, but by the table, whatever they have given with the units and with the justification of this example, you will be able to have some idea about the calculation and the various considerations. Okay. Now, in the earlier case also, we have seen in the first chapter that there are three different methods. There are pressure coding methods, there are direct method, and there are indirect methods of gas content estimation. And in the earlier note 1, we have also seen that if you are going to calculate the gas in place or the gas content calculation, there are three types of parameter. Okay, you can also see I have highlighted the total gas content is the sum of the three different components, which are the first is the gas content due to the lost gas. Okay, when you are going to put the sample into the canister. The second item is the measured gas content, which is the dissolved gas content, which you are going to measure in the disruption canister. And the third one is the residual gas content, okay, which is being there after the total disruption is completed, and you have to crush the sample, and then you are going to measure the residual gas content. So whenever you are going to estimate the total gas content, as we are not going to actually determine this, actually you are not going to calculate, that's why we are going to use the term estimation. So the sum of the total gas content is sum of the lost gas, measured gas, and the residual gas. Okay. Now, the different cases for all these three different parameters are going to be governed by the different parameters, and there are, depending on the method you are going to use, there are different types of errors. Okay. The one I have shown you in the uncertainty principle in the appendix, that is totally based on the laboratory measurement. Okay. Whatever I have shown the uncertainty errors analysis by Mavor and Ozdemir principle, that is directly related to the laboratory principle, that is directly to the laboratory measurements. So now this is related to the field measurements. Okay. So obviously there will be some deviation, there will be some different components. Okay. So now let us see what are the different type of error. This figure, what you can see in the coal gas recovery geometry, this thing also I have discussed. Why this is required again? Because of the identifying the parameters. Okay. Now let us start with the gas in place estimate errors. If you are going to analyze the gas in place, or if you are going to estimate the total gas in place, obviously in the field, so what are the sources of errors are present, and what are the amount of the error that you need to estimate? Finally, you will be giving the accuracy with plus minus some error value. Okay. Now, as you have seen that there are the other four parameters, the drainage area, the thickness, the average in situ density, and the average in situ gas content. These four are the parameters. So we have to see the errors in these four parameters also for measurement of this four parameter. Okay. Now the first is the drainage area errors. You can understand by this time what is the drainage area. The drainage area means with the borehole network, okay, and with the in situ network of the permeability and the fracturing open channels, or or the natural gas discontinuity, whatever natural discontinuity is present into the rock, that will give you the total pattern. And as you know that this drainage area is also going to be dependent on the type of the rock. Okay. The typical concentration and the different type of rock types. Okay. The presence of the water body, whether it is aquifer, there is a nearby lake area, or what about the softness of the rock and about the grain size. Because if it is a fine grained, the porosity will be very much less. If it is the coarse grained of the rock, the porosity will be much higher, and this will be giving you the open channel source to the flow of the flow through the rock. Okay. Now, if you are going to consider this area again, please go see this figure 2.1. If you see this figure, then depending on the type of the rock or type of the geometry, as you can see, there are different variations for three different wells. Suppose this is your concerned area for drainage, okay? But in this case, you can see that there are a lot of heterogeneity. There's a lot of differences of the seam thickness, of the coal thickness. There are a lot of differences of these fractures, the orientation, and there may be some faults and the other layers. So based on the whether there are fine grained or whether there are the coarse grained. So based on that, you have already seen earlier that there are structural and the stratigraphic changes in the reservoir. Okay, there are the structural and the stratigraphic changes throughout the reservoir. So obviously, whenever you are going to do this estimation of this drainage area, you have to have the idea about the borehole logs, because it is only the borehole logs. If you are going to create a map of your area like this, then you will be able to understand that, okay, depending on the depth of the borehole, what is the surrounding situation, what are the surrounding stratigraphy, surrounding rock types are present, and depending on the layer or depending on the discontinuity orientation, how it is going to help you your fluid flow, or how it is going to allow the drainage through the rock. Okay, but again, this is very much indeterministic, because you cannot drill all the places. You just have to simulate the results based on the core log sections, okay, or the laboratory measurement analysis. Now, in general, if you consider the field area, in field, obviously you can take some of the sample from the field from some borehole. But if you are going to estimate the total drainage area in the field, you have to do some seismic interpretation. What is seismic interpretation? You know that you are going to send some acoustic signatures, okay, and depending on the velocity, the sonic velocities, the primary wave velocities and the secondary wave velocities, and they are again going to travel certain distance, and again in the receptor it is going to be recorded. So from that records, you will be able to calculate that what is the velocity of the P wave and the S wave in the different rock types, and from there you will be getting some idea about the different rock types and their different stratigraphic compositions. Okay, so this is the way by which you are going to measure or estimate some of the drainage area pattern. Okay, the second point is the gross coal thickness. The second point is the gross coal thickness. You know that the coal thickness is not, if it is a sedimentary deposits, and if the all the beds are horizontal, so then you can see that it is more or less nearly horizontal beds are moving. Okay, so their deep will be zero, but deep, even if the deep is the zero, the thickness of the bed, thickness of the coal seam is not same everywhere. Okay, there may be some intrusion, there may be some other type of the beds coming. If there is a fault zone, then the beds are going to be upside down or down or up, going up or down, depending on the whether it is a normal fault or the strike shift or the reverse fault. Okay, and obviously, as the coal thickness is not going to remain same, obviously if you see the borehole log section, you will be able to get the idea. So you have to consider the average thickness. Okay, and whenever you are going to consider the average thickness, you have to keep in the mind that whether this average thickness is going to give you the total representation of the drainage area or the seam area or not. Okay, if it is not representative of your total coal seam thickness, then there may be certain error. Okay, so you have to be careful for that also. Next is the average in situ density. In situ density means the field rock type and the in situ density, whatever the rock type is present. Now, for this thing, you must know that in your rock mechanics studies also, if you are going from surface to the 20-meter or 30-meter zone, you will be getting loose soils or the loose rock types or very clay materials like this. Okay, and then only you will be experiencing layer by layer soft strata or the hard strata, or depending on the succession, the stratigraphy of that particular area. Now, if you know the stratigraphy of that area, you know that what are the different rock types are present. And so depending on the rock type, the in situ density is also going to change. Okay. just like the if you have done the reserve estimation, you know the assay value. Okay, do you know the assay value? Anyone, you understand what is assay value is called? Anybody is there? You understand what is assay value?
Yes, sir.
Okay. So if you understand the assay value is going to give you the grade of the deposition of this individual rock type or the ore zone. Then like that same principle, you will be able to get different rock and their density values. And so you have to calculate the average in situ density. Okay, average in-situ density by taking about all these beds that is intercepted by a borehole. So once you are going to do the interception, you have to see what are the different coal beds and what are the number of the coal beds and the average density. The coal density, you know, the coal density is varying from 1.1 to 1.4 gram per cc. Okay, this is the average coal density. Or if you are going to consider the ton per meter cube, it is given in the 2.3 ton per meter cube. This is also the coal density. But then for the fractured coal, for the fine powdered coal, if the coal sample is broken, its density may go as high as 1.6 or 1.7 gram per cc. As you can see also that in some results from the other CBM reservoirs is going to give you the idea of the density as 1.5 to 1.85 gram per cc. Because of the broken coal, it is going to consider much, it is going to consider much of the mass and the less volume. Okay, so the density is going to be higher. Okay, somewhat. But then depending on the size range, depending on the coal seam, you have to consider an average density. So if you are going to see these borehole logs and then gamma logs, okay, gamma logs on the or the some acoustic signature, so from there you will be able to see what are the different rock type presence, and from the gamma signature also you will be able to see that whether whatever signature is going to give you the idea about the rock type, these are all the real value, or you are going to take this value as it is observed, or you are going to do some averaging. Okay, so the average in situ density is also required. The next sources of error is the gas content error. Okay, the gas content error, you know that whenever you are going to measure the gas content, okay, the gas content when you are going to measure, it is based on three different components. Now the lost gas, the measured gas, and the residual gas. Now depending on the type of the method, you know that there are three different methods. There is a pressure coding technique, there is a direct method, and there is an indirect method. So based on these three different methods, there will be chances of the error. Again, whenever you are going to do some analysis, if you are having some earlier data or if you are having some benchmark data, okay, what is the benchmark data? Benchmark data is that you have analyzed and you have seen some of the data, you have measured some of the sample from that reserves, and that graph is with you, some isotherm graph or some gas content value which is already tested, that data is already there, so that will be giving you the bench value, okay, the benchmark value. And then whenever you are going to do the disruption canister testing, you are going to measure different sample and you are going to check whether your disruption canister testing results are going to match or are going to be in the close proximity of 10% or 15% to the accuracy of that benchmark value, and based on that only you will be able to consider those values. Okay, to show you how this benchmark value can start, you can see that in this table, okay, they have done some direct method analysis by some borehole and there is a benchmark gas content. Okay, benchmark type, from the pressure code they have established some isotherm, they have received some absorption isotherm data, and from there when you are so there's a graph which is giving you the idea that at particular temperature, at particular pressure, you will be able to see how much is the adsorbed value. Okay, now, whenever you are going to do some direct analysis and you are going to do this direct method and you are going to put this sample into the disruption canister, you are going to start the disruption canister testing, whatever value you are getting, obviously depending on the sample there will be some nominal variation or there will be some huge variation of this data. So now if you are going to see that your recorded resorption constant results are within the 10% or the 15% of this benchmark data, then you can rightly say that whatever our measurement techniques we have done, this is more or less okay, and we can take those values for the calculation, and these are very much less error. Okay, this is having very much less error because our main disruption isotope, whatever we have got by the values we have got by the disruption constant and whatever the benchmark value we are having, these are more or less matching closely. But if it is not going to be fulfilled, then obviously you have to take some calculation. Okay, you have to do sometimes the results from the disruption canister depending on the coal sample, depending on the loss gas estimation, depending on the residual gas estimation. All these data may give you some overestimated results or underestimated results. Okay, so you have to be very careful, and at each defined parameter, suppose the technique you are going to apply, the basis you are going to apply for the calculation, these things will change the calculation. Okay, now for the method, you know that there is a direct USBM standard method of which I have discussed, that you are going to take the coal sample, the pressure coring direct method, and the indirect method I have already discussed. In the direct method, in brief, let me explain again. In direct method, we are going to take a core sample, and then after taking this core sample into the core barrel, we are going to take it in the surface, and immediately we are going to put it into the disruption canister testing box. Okay, what is the disruption canister testing box? It will be discussed in the third chapter. Okay, so in that disruption canister testing box, there is a pressure gauge which is going to continuously maintain the pressure, and there will be a thermocouple which is going to maintain the temperature, and from there, as the number of the gas molecules are dissolved, the pressure will rise. So from there you will be able to understand that at that particular pressure how much volume of the gas molecules can take place and what is the total volume of the gas dissolved. Okay, now you can see also that with the direct method there are some variation of this direct method, which is the Smith-Williams method, and there is an Amoco method given after the name and the industry that has used, or the experimental apparatus that is going to generate it. Okay, now I'll be not discussing what is the Smith and Williams method and the Amoco method, because this is beyond your concept. Okay, that is not required for you. But now you must have the idea that there are some different variations, and based on this variation, the Smith and Williams method is going to give you some overestimated results. Okay, where from the actual data, actual direct method, and then the obtained the sorry the Smith and Williams method is going to give you some underestimated results. Okay, it is to be low, and those which are measured by the Amoco method are usually high, so they are the higher estimated or overestimated results. Okay, now those variations are not important, but what is more important is that how much variations is there. That much variations will give you the sources of the error. Okay, as you know that there are the lost gas, there are the dissolved gas, and there are the residual gas. The most critical factor to measure is the lost gas, because of the initial time fraction, because of the how you are going to handle this core sample from the core barrel, and how quickly you are going to put this into the disruption canister and start the experiment. The zero time is very very crucial. Otherwise you are going to lose this technique. Otherwise you are going to have some error. Now if I'm going to open this note also, the note 1 for you, as I have discussed with you, the CVM note 1, let me open it. CVM note 1, yes. If you see the CVM note 1, there is a lost gas value. Okay, let me show you that. There is a lost gas estimation. When you are going to measure this lost gas estimation, the error on this graph. Okay, this is the graph I am going to tell you. This is the same graph about the lost gas method. You can see that if you are not going to understand what is the zero time, you will not be able to understand. This is your sample is put in the canister, and you are going to measure the pressure. Okay, you are going to measure the pressure, no problem, but you will be getting only this. Okay, but how far you have to put the backward, that is only you will be able to understand by putting the stopwatch at the zero time. This zero time is, it is going to be earlier like here, or if it is going to be later like here, your total gas content will be a erroneous one. Okay, so this is the most critical one for the lost gas estimate, and that's why you have to be very very careful when you are going to do this lost gas estimation, because the maximum sources of error generates during the lost gas only. Okay, you have seen this in the note 1, so I am not going to show you or discuss you in a detailed way, just to give you the idea about why it is so important. When you are going to deserve this, you are going to take this desertion test, there are two factors for which the temperature can vary, for which the temperature can impact this lost gas content. How? You know that the gas disruption rate, gas disruption rate means the rate by which the pressure will change. Okay, when you are going to dissolve and start the taking out the pressure, this rate is also going to change with the temperature. This is the first point. And second point, obviously you know that the gas absorption capacity is inversely proportional to the temperature. If you are going to increase the temperature, the adsorption capacity reduce. So obviously, depending on this in situ temperature, this in situ temperature is definitely different than the surface temperature on the or the laboratory control temperature. Okay, and if you have understood in the mine ventilation, underground mine ventilation, you must have heard a temperature called VRT, virgin rock temperature. If you have remembered that virgin rock temperature, so you will be able to see what is the in situ rock temperature means. Okay, that virgin rock temperature can be taken same as the in situ rock temperature. Okay, so this is the first criteria about the temperature that is going to dictate the error. The second is the type of the sample. Okay, you know that the type of the sample is very very crucial, because if you are going to take a sample from a borehole and that sample is not representative of your total coal seam, then obviously this will be not representative. The value whatever you will be getting, that will not be representative for your total seam. Okay, so you have to take several sampling from a seam also to establish the disruption isotherm, and then you have to compare, and then you have to be sure that okay, these values are more or less okay with 10% or 15% of accuracy, and then only you will be taking that okay, this isotherm is the correct one, more or less the correct one. Next is the accuracy of the gas content. Now again, accuracy of the gas content will again governed by these three different processes. Okay, but then what are the limitations of this? Generally, generally whenever we are going to measure this gas content, okay, there are the two different sampling technique. You can take drill cuttings or the broken coal samples, and the second case is the core sample, the cylindrical core sample. You must know the different parameters of consideration. Okay, there are three different methods, then sampling techniques, then the core sample itself is coming. Okay, so the drill cuttings, if you are going to take, you know that drill cuttings are the broken coal sample or the rock samples, and as they are the drill cuttings, obviously these are the broken, and then obviously some amount of the gases is already escaped. So there will be definitely an error for this lost gas component in the drill cuttings. This is the first point. The second point is, if you are going to measure the disruption canister testing with this drill cuttings, there is every possibility that this coal drill cuttings are going to be mixed with some other rock layers, which are obviously not going to dissolve the gas, but then they are going to be considered as the mineral content or the ash content or other material. Okay, which will be doing nothing but the increase the mass, and so in per unit mass, you will be whatever value you will be getting, it will be much more lesser than the actual coal mass. Okay, so these are the two different concepts for error whenever you are going to do this drill cuttings samples. Then if you are going to do the core sample, you know that the core sample should be adequate in size, and when you are going to take the core sample, you have to take every precaution so that you are not going to fracture it, you are not going to lose the pieces, you are not going to escape the moisture, and you have to wrap up so that the no in situ moisture is going to be escaped when you are taking this, when you are going to taking these samples into the surface. Okay. In this graph, figure 2.2 is going to show you the different technique of the methods by measured from the direct methods and by the two different methods, Smith and Williams methods and the Amoco method. You can see that some of the methods are very underestimated and some of the methods is very overestimated. Okay, so the direct method is the most accurate one, which you need to measure it by dissolvation canister, and you have to do the numeral samples, no number, different types of the sample and different number of the samples should be tested to get the estimated results of gas content. Okay. Again, after this, the next sources of error is for the basis. Please mute yourself. Who one is kept open? Please mute yourself. A class is ongoing. Please mute yourself. I don't know why you are opening this mic option if you are not going to be alone. It is creating noises na, for you and others. Now for the define of the basis, okay, for the define of the basis, you already have seen this table, but this table is also replicated here. And why this is so important? Because the type of the basis you are going to utilize when you are going to use this gas content results. Okay. Now in this note, if you read, they have going to give you the idea. They have taken only three bases. First, they are going to take the air dry gas content, excluding the moisture. Okay, and they are going to measure this air dry gas content, and then this basis is to be transformed from the taken the sample from this, taken the results of the multiple samples, and then they are going to convert it in the basis of the air dry data to the organic fraction, because it is the carbonaceous part of the coal which is going to absorb the gases or adsorb the gases. Okay, so that's why from the air dry basis you are going to transfer to the organic fraction basis, and from the organic fraction basis you are going to transfer again this basis to the in situ gas content. Okay, why, what are these meaning of these three? You can see from here, you can see air dry basis, here you can see the organic fraction basis, and lastly you are going to measure at the in situ testing basis. Okay, it is that in situ testing basis you are going to report the gas in place. Why? Because the gas in place is not for the laboratory, gas in place is for the in situ or the field basis. Okay, so finally you have to represent the in situ the in situ gas in place into the in situ basis. Okay, so you have to correlate the temperature at in situ, the pressure at in situ, and the density also. So now you can understand the step-by-step process of the different errors. Okay, whatever the dry and ash-free basis we are going to generally discuss, okay, or we are going to generally allow, this is from the laboratory measurements, and this is used the DAF basis, dry and ash-free basis utilization. This is going to be used to compare the various results from the laboratory basis, or generally if you are going to report the gas absorption capacity of different coals. But whenever you are going to represent the gas in place or the gas content, in situ gas content, then obviously you have to report based on the in situ gas basis. Okay. Now with this, there are different formula is given for the PAR formula. You can see in this here, they have discussed equation 2.2. They have discussed the PAR formula to calculate the mineral matter free basis. But at this point, I'm excluding this. I'm skipping this, and you don't need to read it. You don't need to read this part of the PAR formula. Okay. Now let us going to discuss the final discussion of the chapter is the evaluation procedure, how we are going to evaluate. Okay, so there are in general there are 8 fundamental steps. Okay, and before you are going to evaluate, whatever accuracy the Gas Research Institute GRI research efforts resulted from the improved accuracy of the 4 items. Whatever the accuracy you are going to improve, that is based on these 4 places. What are these? The 4 items. The first is improved gas content estimate from the core samples, which is the first step. If you are not going to improve the accuracy of the gas content measurements or the estimation, your, your evaluation will not be up to the mark. The second is excellent agreement between the ash content estimates from the core and the opal hole density log data. You are having the log data, you will be able to know which one is the coal, which one is the different type of rock, and then depending on the ash content also, you will be able to consider what is your total density of the coal. If there is a much number of the more quantity of the ash, obviously the coal density will lose, it will be reduced. Okay, so you have to match this density log data and the measurement of the density for the coal sample. The third point is that high correlation between the gas content estimates and the inorganic content of the multiple samples. Gas content estimates, obviously whatever you are going to get, it is based on the organic content. Only the carbonaceous matter will be able to absorb the gas or absorb the gas, whereas the inorganic content will give no such addition for the gas absorption. So you can totally separate that. Okay, so if you are having the data from the multiple samples and whether your gas content results, whatever you are having, the isotherm test, okay, it is also based on the inorganic matter free or the organic matter free you are, if you are having, then you have to correlate that. And finally, whatever the including gas content within the both coal and the carbonaceous shell in the gas in place estimate. Now the shell is the defined rock type, obviously. So I have also told you earlier, given you the idea when I have going to give you the different reservoirs, that the coal, the roof layer and the floor layer are generally in the coal seam are having the sandstone and the shell. Whereas sandstone is not absorbable, sandstone cannot absorb the gas, but shell can absorb the gas. But the capacity of the shell is much more lower than the capacity, gas content, gas absorb capacity of the coal. Okay, and the porosity of the shell is much more lower than the coal also. The coal, the minimum pore size of the coal may be in the 5 or 10 nanometer size, whereas in the and very less amount of the pore size in the coal is in the micropore range. That means most of the pore sizes in the coal are in the mesopore or the macropore, which is having more than 2 nanometer. Whereas for the shell, it is the maximum pore sizes in the micropore zone. Okay, there is very high amount of the pore sizes into the less than 2 nanometer zone. So for that, obviously the pore sizes are less. So obviously the pore capacity, the gas absorber capacity will be much more less. Okay, so you have to correlate that also. If in your coal seam there is a some amount of the shell, so you have to have some data of the shell gas estimates also. Okay, so that you can correlate that, okay, this part is the shell, so obviously whatever result I am getting from this shell adsorption, that is going to be matched by some earlier data, earlier historical data or earlier gas adsorption data. Okay. The next is the gas in place methodology, which relies upon the 4 critical components. Okay, how the gas in place methodology are going to be improved based on the critical component. What are the critical component? Let us see now. Performing the desorption measurements on multiple core samples at reservoir temperature. So whenever you are going to take the coal sample and you are going to put them by the desorption canister testing, you have to take different core samples representative of the seam, and then it should be done on the reservoir temperature, not the surface temperature, not some laboratory temperature which is going to be very much higher from the reservoir temperature, because you will be going to get some overestimated or underestimated results of the gas adsorbed volume. Second point is the relating the sample gas content to the sample composition and the density. Now, depending on the sample density, you can know that, okay, you are going to measure the density and then you will be able to see the density measurement. But the type of the sample means, again, the rank, the grade, and the purity. These 3 things will come. Okay, the composition, the type. sorry, the type, grade and rank. These three things will come. So you have to relate, correlate. Okay. Estimating the in situ gas composition and density from the density log data. Whenever you are going to get the density data from the sample analysis by the Boyle's law or the by the data I have shown you, okay, by the gas helium gas inclusion, and whatever data you are going to get from this log data from these gamma logs, if there is a matching, then obviously your error part will be taken care of. Okay. The last one is the converting the measured gas content estimates to in situ condition. Whatever the measured gas content you are going to do by the laboratory or by the disruption canister testing, if you are going to do the disruption canister testing, you are going to do at the surface temperature. But if you are going to replicate it, you are going to correlate with the in situ gas temperature, you have to again apply the temperature correction. And obviously, whatever the reservoir pressure condition by the vertical stress or the horizontal stress condition you are going to measure, you have to do this analysis based on the in situ pressure condition. Okay. So these are the some steps and the critical observations you need to consider. And then finally we are coming to the 8 important steps by which we are going to perform this gas estimation. Okay, let us see these first 8 steps. First is that perform the gas disruption measurements at reservoir temperature on conventional or wireline retrieved core sample. So now this is going to give you the idea about the temperature and the type of the sample you are going to do the testing. Okay. The second point is estimate the total gas content of each sample using the direct method and the lost gas content procedure. Lost gas content procedure, you have seen that. Direct method will give you the idea. So for each of the type of the sample, you have to estimate the lost gas content more accurately. Okay. Third point is the relate the total gas content of the multiple samples to sample composition. Now suppose in a particular seam, in a particular coal bed, okay, you can get the different type of the coal samples depending on the structural heterogeneity, depending on the depositional heterogeneity. You may get that at one point you are going to get some high volatile bituminous sample, but at some other point you are going to get anthracite coal sample or some lignite coal sample. So obviously their absorbed capacity will vary. So you have to correlate. You have to say that okay, this is the same type of the coal, but the rank is different, and so we are going to get the defined higher ranks, higher absorption capacity. Okay. Relate the sample composition to the density. Sample composition means whatever whether the density, that means whether the rock is very much hard or whether it is very much soft, whether it is very much porosity is present very high, whether it is heterogeneous or homogeneous, what are the different type of gas inclusion or not. So sample composition will be observed and it is going to be related to the density. And you will see that the density value is also going to change from 1.1 to 1.4. Sometimes it is coming very high. You have to exclude that. You have to remove that coal particles from the analysis. Okay. Next, determine the in situ moisture content from the laboratory moisture measurements. In situ moisture content, there is a standard procedure. In situ moisture content, why it is required? You can do in the laboratory testing by dry sample analysis or by the moisture saturated or the wet sample analysis. But if you know that okay, in your in situ moisture there is only 70% of the moisture, there is only 40% of the moisture, so you have to convert that results to represent the in situ moisture measurements, and you have to correlate that also. Okay. Next is the estimate the gross thickness and the average in situ density from the open hole density log data. Why this gross thickness and the density log data will be recorded? Because the gross thickness will give you the idea about the coal sample thickness, which is going to be taken care into the equation of the gas in place calculation. If you are not going to consider this variation, and based on the density also, if your density is becoming very much high, then you have to assume that in this coal sample there is some other material is also present, so you have to exclude that. Or if it is falling much less than 1.1, then also you have to exclude that. Okay, because there is some other sand particle or some clay particle which is mixed within the coal, and so you cannot take into the consideration this coal sample. The seventh point is the compute the in situ gas content at the average reservoir density and the moisture content. Now, whenever you are going to measure the reservoir density, you have already have calculation, you have already done the calculation for the reservoir density from the variation of the depth, okay, and average density based on the different rock type data and the moisture content of the reservoir. So now you are going to calculate the gas content based on that much of the percentage. So now it will be going to represent your actual in situ gas content, not the surface or the laboratory measurement gas content. And then finally compute the gas in place volume and with the equation 2.1, the first equation, the gas in place volume, which will give you by the reservoir drainage area and the density, average density. Okay, this is the equation, the average density, drainage area, the depth of the reservoir thickness, and the average gas content. Finally, you will be able to estimate the in situ gas in place. Gas in place is always referred to the in situ, okay, because you are going to measure the gas content in the in situ, not in the laboratory analysis, okay, not in the laboratory second sample. So this is going to give you the idea about some of the sources of error and how you are going to tackle them and how you are going to proceed for the gas content analysis. Okay. In the next class, I'll be going to discuss you only some of the methods, some of the direct methods, just like the disruption canister testing. This has to be discussed. And only some part of this third chapter I'll be going to discuss with you. And finally, I'll be discussing with you some of the papers, which will be done by in the next 3 or 4 classes. Okay. So any questions with this? Your second class is second chapter is done also. If you are having any question, you can ask me.